A steam engine operates by converting thermal energy into mechanical work, governed by the fundamental laws of thermodynamics. The process begins with the combustion of fuel, which generates heat that is used to boil water. This creates high-pressure steam with substantial internal energy. The pressurized steam is then directed into a piston or turbine, where it expands and pushes against mechanical components, performing useful work. During this expansion, the steam's internal energy decreases, aligning with the first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed between forms such as heat and work. However, the second law of thermodynamics introduces a critical limitation. Not all the heat energy absorbed from the fuel can be converted into work. A portion must be rejected to a colder reservoir, typically in the form of exhaust steam. This inevitable heat loss constrains the engine's overall efficiency. The maximum theoretical efficiency any heat engine can achieve is defined by the Carnot cycle, an idealized, reversible cycle consisting of two isothermal and two adiabatic processes. The Carnot efficiency is given by the formula eta equals 1 minus Tc/Th. Here, eta represents the efficiency, Th is the absolute temperature of the hot reservoir, and Tc is that of the cold reservoir. This equation illustrates that efficiency increases with a greater temperature difference between the two reservoirs. However, for a Carnot engine to reach 100% efficiency eta equals 1, the cold reservoir would have to be at absolute 0 or 0 K. A condition that is physically impossible according to the third law of thermodynamics. Therefore, a perfect engine with no heat rejection would violate the second law, which states that a cyclic heat engine must always transfer some heat to a cold reservoir. In reality, steam engines operate on thermodynamic cycles like the Rankine cycle, which incorporates the practical limitations of fluid properties, friction, and heat losses. These real-world cycles are inherently less efficient than the idealized Carnot cycle due to irreversibilities and non-ideal fluid behavior. Despite these limitations, steam engines played a pivotal role in the Industrial Revolution and continue to be foundational in power generation, where thermodynamic principles guide their design and optimization.